Hi everyone, this is Dr. Baby Shalini, Associate Professor, Department of ECE, Rohini College of Engineering and Technology. In this video, we are going to see about the basic electronic components, capacitors. So the capacitor is a passive component that stores electrical energy. A capacitor consists of two or more parallel conductive plates which are electrically separated by air or by some form of good insulating material. This insulating material could be wax, paper, mica, ceramic, plastic or some form of liquid gel as used in electrolytic capacitors. When used in direct current or DC circuit, a capacitor charges up to its supply voltage but it blocks the flow of current through it because in between the parallel plates we are having a non-conductive dielectric material which opposes the flow of current from one plate to another. However, when a capacitor is connected to an alternating current or AC circuit, the flow of current appears to be passed through the parallel plates and it will be appearing at the other end. So, now let us look into the systematic representation of a capacitor. So, we are connecting or we are placing a dielectric material between a positive plate and a negative plate. The positive charge is represented as plus Q and the negative charge is represented as minus Q. So, between these two conductive plates, we are placing a non-conducting material which is dielectric. And the symbol used to represent capacitor is two parallel plates as shown in this figure. So the general equation of capacitance is it is the ratio of charge per volt. So charge represents the amount of charge that is stored in the plate, that is Q, dividing by the total voltage that is applied across the parallel plates of the capacitor V. And according to the dimensions of the capacitor, we can write the capacitance as epsilon A by D, where epsilon is the dielectric constant of the material and A represents area of the parallel plates and D represents the separation distance between the parallel plates. So now let us see how the equivalent capacitance is calculated when the capacitors are connected in series. So let us consider this diagram. So across a supply voltage V, we have connected three capacitors C1, C2 and C3. So in the series combination, across each capacitance, we have a different voltage V1, V2 and V3. And these drops is equivalent to the total supply voltage V. So that we can write the equation as V is equal to V1 plus V2 plus V3. So now we know that voltage is equal to charge per capacitance. So the total voltage V is equal to total charge Q dividing by total capacitance CT. Now across each capacitance the voltage V1 equal to Q by C1 and V2 is equal to Q by C2 and V3 is equal to Q by C3. Now when we substitute these voltages in the first equation, we get Q by Ct is equal to Q by C1 plus Q by C2 plus Q by C3. When these Q values are taken as common in the both left hand side and right hand side, they cut each other. So remaining we are get 1 by Ct is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So that is the total capacitance when the capacitors are connected in series. So from the last equation we know that Ct is equal to reciprocal of the parallel combination. So now let us consider what will happen when the capacitors are connected in parallel. So we know that capacitance is equal to Q by V. Q by V, so C1 equal to Q by V, Q1 by V, C2 equal to Q2 by V and C3 is equal to Q3 by V. Now the total charge Qt is the sum of all the individual charges. So Qt is equal to Q1 plus Q2 plus Q3. So if we substitute the values of Q from the above equation, then we get CTV is equal to C1V plus C2V plus C3V. So if all the V's are taken common and they cut each other, then remaining we are having Ct equal to C1 plus C2 plus C3 and so on. So this is the total capacitance when the capacitors are connected in parallel.